Our speaker.
Hi, I'm Howard Gordon, and everybody calls me Flash. Spent most of my career at NSA and invite my friends to these talks. And I'd like to introduce our speaker today is a distinguished professor and founder of the Department of Data Science and inaugural director of the Institute of Data Science at New Jersey Institute of Technology. He is a Hall of Fame inductee at University of Maryland School of Engineering. He advises the White House, and he has a close connection with IEEE. So, and I know him mostly from his talks at supercomputing conferences. So, Dr. Bader will be talking on accelerating artificial intelligence through high-performance computing.
Thanks, Flash. Well, it's nice to be here and talk with everyone. And I have to say, it's nice to see a couple old friends, long-term friends here on the Zoom. And I first got into parallel computing probably in the early 1980s, 1982 or so. And I was getting a lot of help on Usenet groups and online. Then many years ago, many years after then, when I started collaborating very closely with NSA, I realized all the people I was talking with were actually some NSA employees. So it was great to work with those communities that were really leading the way in high performance computing. I did my PhD back in 1996 at University of Maryland, College Park, and really that launched my career. And my degrees are all in electrical and computer engineering, not in computer science, but it was a perfect preparation for me to work in areas of high performance computing, supporting a number of federal agencies and types of applications. And also, I'll tell you a little bit about some of the work that I'm doing today using tools that we're building out with Department of Defense, but using them for problems in neuroscience and understanding the brain connectome. So there's a bunch of things in this talk, but I'll also tell you a bit about high performance computing and its relationship to supporting the AI revolution that we're seeing today. I also want to mention that here, just on some bullet points, I received one of the highest computing awards from the IEEE called the IEEE Sidney Fernbach Award. And that's because in 1998, I built the very first commodity-based supercomputer that is really the model that we use today, using Linux as the operating system and commodity processors and components for a lot of the supercomputing that's also driving a lot of the AI revolution that we have today. So it was mentioned that I'm at NJIT. I moved here about 6 years ago after founding the School of Computational Science and Engineering at Georgia Tech, where I had been previously. So NJIT is located in Newark. I have an Institute for Data Science that's located in Jersey City. Recently, NJIT announced that it's devoting over $10 million for its push in AI. And this is very similar to every university, every company out there is trying to figure out what's happening with AI and how to invest in it. What are the right strategies? What does it mean? How does it change everything that we do internally? How do we train people? How does it change the applications across various sectors? So we're seeing the most amount of change ever in technology in the last 2 or 3 years than we've ever seen in the history of technology. So the rate of change today is just so fast. NJIT, for those of you who don't know, it's a public technological university. Recently, the Wall Street Journal, for instance, in its College Pulse rankings, named it the #2 public school in the US. If you look at public and private, I think we're about number 19 on the list. But if you look at just public schools, they thought that we were number two, and that's really based on the students that we produce and their ability to move up the socioeconomic ladder. And then in terms of students, we're really growing gangbusters in terms of students who come out with computing expertise. So we're graduating every year about 1,000 students or more. We're the largest program in computing in the tri-state area in terms of our graduates. And in fact, we just recently overtook engineering at NJIT for our size. Now, those of you who are really interested in physics, that's housed in our College of Science and Liberal Arts, which has a pretty significant physics um, faculty. In fact, NJIT runs the Big Bear Solar Observatory that studies solar physics, and that's located in California, but all the data is shipped out to New Jersey for doing the processing and the algorithms on it. I run an institute for data science that has a number of centers associated with it. And just very briefly, the centers are in areas related to big data, cybersecurity, medical informatics, and also AI and machine learning. So our faculty are typically organized within these centers, and we do a fair number of projects for outside agencies and companies. My institute has an advisory board, um, most of which is pictured up on the slide, and we're advised by folks coming from all different sectors, from transportation, from tech companies, from biomedical, manufacturing, financial services, and more. So it's quite a broad set of application areas that we look at represented by these folks. And recently we started a new master's degree program in AI, and I think you'll start to see a lot of universities out there offering more and more in terms of data science and AI. In fact, I helped found our new Department of Data Science in 2021, and we're one of the first universities offering bachelor's, master's, and PhD in data science anywhere in the country. So Flash and Donald asked me to give this talk about high performance computing and AI, large language models. So I thought, what's best to do but go out to ChatGPT and ask it, well, what should I talk about? So here's the image that I got up. This is generative AI. I'm trying to explain large language models. So you'll see it's so it looks like a nice graphic, but if you start to look at the text in here, um, it's getting things that are statistically right, but are kind of gibberish. And here's the prompt I used. I wanted an informative and visually engaging graphic for a PowerPoint presentation explaining what a large language model is. The graphic should show a JPEG. So I thought, well, this doesn't cover high performance computing. I know we have some HPC, high performance computing or supercomputing experts in the audience. So I asked for a graphic explaining the confluence between large language models and HPC, and you'll be happy to see this also quite meaningless generative AI image. How to interpret it, your guess is as good as mine. But it looks kind of interesting in a statistical sort of way. But again, it's kind of a bunch of gibberish coming out. So as we're moving into the era of AI, what AI is able to do is really learn statistical patterns across massive, massive data sets. And to do that, we need algorithms, we need training data, we need supercomputers, and all of it coming together so that we're able to learn those patterns and then, given a prompt, be able to produce something from that model that is statistically um, quite good, hopefully even better than humans in some cases. So you've probably heard a lot about large language models. this is the next couple slides I've borrowed from lifearchitect.ai that has some pretty good graphics about what's happening with these. Many of the initial models that people talked about, like Meta's Llama, um, these were ones that you could download and run on your own computer. And you could think of these in terms of size as maybe a paper plane that you went to fly. These are small, you can test them out. You can put them on your laptop, but they're quite small in size. The second type in the middle here is more like a little Cessna plane. And these are also hosted. You would own the model, but they're a little bit bigger. Maybe they're a little bit more specialized, and maybe they're trained on some specific data for an application that you're trying to use it on. But the ones that we hear the most about are probably in scale like this Boeing 787. These are massive, and you wouldn't have these on your laptop. You'd only be able to access them through the company's API. For instance, this is like OpenAI's ChatGPT or Anthropic's Claude or Google Gemini, where maybe you have least access, but really just an API to be able to access that model that's been built. And this is really what's getting all the attention, all the rage today, is to understand what these types of models can do.
Is it okay to jump in and ask a question, or is that
Sure. Yeah.
when you say large, medium, small, that kind of thing? What number of is that by number of parameters in the model?
Um, in some sense, yes. Large, medium, small is all relative. Um, so I expect that what is a large model will continually grow at some rate. For instance, a large model um, 2 years ago might have had, say, 100 billion parameters in it today, or 100 billion parameters in it. Today, a large model may have 2 trillion parameters in it. So the notion of what's large will continue to grow at some rate. And all I mean by large is those are the ones of most interest where the internet and all public data, maybe even not public data, has been sucked up and used to train these models. The mechanisms for training for these models is fairly similar, whether they're small or large. It's just what data sets did you use to train the model? What were the parameters that you used on the model that you wanted to train, and so on. The biggest models here, they're called frontier models often, and those are the ones that are like the ChatGPTs, Grok from xAI, Elon Musk's company, Claude from Anthropic, Google's Gemini, Meta's Llama. These are the biggest models, and in fact, most of these are trained with NVIDIA GPUs, so a graphics processor, or actually massive numbers of GPUs are used in their training. And they're not static. Usually these companies will have a model and it may take them a couple weeks to train the next version of the model. Maybe there are improvements, efficiencies, more data sets. And so often the model is updated about once a month or so for these frontier models. There's also hundreds and upon hundreds of other models. I have some of them listed in here. Some are very small so that they could fit on your cell phone. Some are maybe medium size that they could fit on a laptop. But the ones that are getting the most interest today are really the ones that are these frontier models that live often in a supercomputer and need a supercomputer to train and to use. Now, this chart is maybe 6 months old, but it shows some of the top models. And on the left are the models in terms of their AI capability. That's the AI score that you see on the fourth column. Or on the right-hand side, the data sets for training that is how they're ranked on the right-hand side. So maybe if I take the right-hand side and just take the first one, Gemini from Google is trained on 130 terabytes of data and is a model that contains 30 trillion tokens. So that's certainly quite large. And then going down this list, you see training sizes. For instance, GPT-4 from OpenAI is trained on 40 terabytes of data and has 13 trillion tokens. So these aren't just in the US. For instance, Ernie, you see on the slide on the left-hand side near the bottom, that's a Chinese company called Baidu. And as you look at the AI labs in here, you see companies that you probably recognize like Google, Anthropic, OpenAI. But there's also quite a lot of other companies that are in the business of doing these large models. And again, the capabilities have been really, really escalating as we get to these large models. Some of the smaller ones from just a couple years ago would be able to do things such as what we see on the top row, maybe doing some arithmetic, maybe debugging simple code, maybe some comprehension of reading. As we start to get to larger models, maybe a large model may be able to do some more elementary math, some causal judgment. Their capabilities start to grow until we get into these extra large or these frontier models where they're solving college level exams. They're able to build full applications, do spatial reasoning. They're able to write and debug code and applications and more. So the capabilities that we see as we get to more and more tokens in the model and training on larger and larger data sets are really where we start to take notice because these models can start to do things that are certainly what we thought only humans could do previously. Now, there's a lot of caveats to that because these models are not perfect. They're really doing large applied statistics of what token would you expect to see next with massive, massive numbers of tokens. And so what happens often is these models do hallucinate. You get something that looks right. However, in reality, it may be something completely fictitious. For instance, several people now have argued cases at the Supreme Court, and in their arguments, they cite case law that was hallucinated by an LLM. So just because we get things that out of these models that look good doesn't mean that it's any good. In fact, my prediction is that we'll get through the hype of these models soon, and we'll probably start to see some colossal failures as people rely on these models for physics and for manufacturing, developing codes, and more in critical systems where everything looks right, but it turns out that there's some core fallacy or something that it made up that just wasn't right. In fact, these models don't know how wrong or right they are. Sometimes, or actually, I would say often, they'll give you out an output and you'll ask, how confident are you in this output? And the model will often tell you 100%, I'm fully, fully confident, when in fact it's just lying through its teeth. So these models are great in some areas, but we have to really recognize that they're not yet fully trustworthy. We don't get explanations for how they reasoned about what they're doing. So where they work well, they work quite well. But I always feel that you need a human in the loop to be able to evaluate what you're getting out and is the use case appropriate for these models.
Yeah, I had a question, Vinod here. So you just said that it's very hard to kind of say right at get-go if what the output is makes sense or not. So are there, so far, do we have some experience like these are a few areas in which they are almost 99% reliable, and these are others where we have to take with a grain of salt?
No, we don't. So these models, you have to remember, they're massive. You can go to Claude or ChatGPT and ask them questions along the whole gamut of everything from science to entertainment to art, literature, writing, anything that you want. And you can evaluate, for instance, you can give them college exams and see how they score, but we don't really understand or have a good relationship between how big the model is, how they're trained, how well they work. It's really all ad hoc at this point. So
Thank
I
you.
mean, for instance, in my experience, I've started to use Claude from Anthropic for programming and actually doing parallel programming, and realized after getting frustrated with ChatGPT that some of the latest models from Claude worked extremely well to be able to take an idea that I would write in text and get some high performance C code that could parallelize for OpenMP, MPI, NVIDIA GPUs, and so on. And that it's just anecdotal that the more and more um, time I spent with it, I had more confidence that I was getting something that worked well. The code compiled, it ran without crashing, and gave me the right answers. So I just kind of get more and more confidence that maybe, for instance, Claude would help me in my particular programming much better, but maybe you're programming for an app on a cell phone and your ability to use it may differ.
Yeah. Okay. Thanks.
Now, what's really, well, here's a slide looking at some of the top models, and this describes some of the training that takes place. So what happens is that a organization gathers as much data as they can find to do the training of these frontier models. So they scrape the internet, they get public databases, sometimes they get um, copyrighted or private data. We're not sure for all of these companies. And what you see here in this list is when the training ended for the model. Um, this goes from the oldest models at the top to the newest models on the bottom. The chip type, so in most of these cases, these are NVIDIA A100 or V100 GPUs. And in some cases, the TPU V4 or the TPU V6 comes from Google, which makes sense because Gemini is Google's model. You see chip counts. So in many cases, they're using 10 or tens of thousands of GPUs. You see the wall clock time for training, everything from 2 weeks to about maybe a third of a year, so 4 months to do some of the training. Total time in years. So some of these, if you look at maybe um, the sequential time that it takes multiplying the training time by the chip count, you'll see some of these would take millennia to train on a single core. So it's just substantial amounts of training time. And retail US dollars, like how much it costs. What you notice is just for one training session of these models, you could be spending $500 million, maybe down Grok 3 from XAI, $1.2 billion. That's Elon Musk's model. 50 days to train and about 32 millennia, 32,000 years of time was taken to do the training. So these aren't things that you would typically just do at home or in the office. You really would have to have a substantial investment and probably a market for what you're going to do with that model to do this training. And remember, this is just one iteration of the model. Most of these companies or some of the models on here, Llama 1, 2, 3, etc., these are investments that are stacked on top of each other by the same company, Meta, doing them. or Gemini, and Gemini 2 also is coming from Google, stacking the costs and so forth. So the lead companies such as OpenAI doing the the GPT model, the leading companies are spending billions of dollars, and about 80% of the GPUs made by NVIDIA goes to just 5 companies, mostly doing this training. So if you look at the news, I think I saw yesterday, President Biden just released an order that allows the federal government to lease private land around the United States in order to run data sets to do AI training, if I read the headline well. I may have that slightly wrong. I didn't look at the details of the order, but right now everyone is struggling to figure out where can I quickly put up a data center that is able to house these types of architectures to do this training. Any questions before I move on?
I have a
So,
question. I have a question.
sure.
Are they able to build upon the previous model? In other words, was Gemini 2 built upon Gemini 1? Are they able to use some of what has been done before? Do they really have to start over again
My
because they have more data?
understanding, many of the companies clearly don't share what they're doing, but my understanding is yes, many of the models, they can take a model that they had previously and use with these transformer models, they're able to augment them and build on top of them. And many of the leading models aren't really just one monolithic model. They really have different components to the models. They may be training sub portions of the models and so on. In fact, when you ask a query to ChatGPT or to Claude or these other models that you can access through a website, you may actually be going through multiple models that are trying to understand or reason about your query in order to get your answer back. So they are certainly leveraging what they've trained on before. Um, and on top of that, they're doing a lot more work in order to create much, much bigger models. So for instance, they're going from at first there's 100 million parameters, then billions of parameters. Now some of the largest models are trillions of parameters, and that scale really dwarfs the previous model sizes.
I'd like to ask a question. You've used the word model, and so what I have in my mind is pictures of neural nets with layers and nodes and thresholding functions and all that. Is that what you mean when you say model?
Yeah, and in fact, the model really you could think of as a big matrix, a dense matrix with floating point values.
Yep.
That's those parameters or entries in that matrix are going to be the weights on the different edges in that neural network structure.
Okay, good. Thank you. I just wanted to make sure I had the right picture in mind. Thank you.
Yeah, that's exactly it. Now, what people have learned is that the 64-bit and 128-bit floating point that we need in scientific computing is overkill for training these models. So there's actually a race to the bottom to say, well, I only have so many billions of transistors on my GPU. Rather than do 64 or even 32-bit floating point, would it still work as well if my numbers were 16-bit or 8-bit or even 4 bits or 2 bits or 1 bit? How many bits are needed? And it turns out in this training, you don't need a lot of bits. That in many cases, we're getting more use of the hardware by allowing them to do smaller word sizes and floating point. And the key operation in the training is really dense matrix vector multiplication. We're just doing a lot of matrix vector multiplication on very small matrices and word sizes. We just need, beyond trillions of them to do the training. So the training is very regular. There are many companies that are building architectures that do nothing other than countless numbers of simultaneous matrix vector multiplications on small word sizes. Any other question?
One question, there's an old computer saying of garbage in, garbage out. Is there any effort by any of these machines to qualify the data before they enter it into their training?
Yeah, I mean, many of the leading companies have done a lot of research to decide, is there data that's useful for the training or not useful? Early on, they had to decide whether or not to include things like the Urban Dictionary or not. There's a lot of thought about what's going into these data sets, or is there data that they don't really need to train on? But if you look at the sizes, when you're training on, I think it was 130 terabytes of data, like Gemini, can you really spend the time to go through that data set and see what you should train on or not? So as we get to these massive sizes, I think what's really happening is that they're just collecting as much data as they can find to train on.
I had a question. So, when they train on the neural networks, is there any preferred architecture like recurrent neural networks or convolutional neural networks or anything which is better? They have found it is better for this training than others.
Well, these large models, I think what happened was there's a paper on transformer models that really changed the game for these large language models. But then there's countless papers on different types of models to use, and that's really where research is at today, trying to understand for particular applications what's the best models to use.
Okay. Thank you.
There's countless variants of models. In fact, today people are training for these LLMs. There's probably thousands of models out there.
Yeah, I got a question. Go back to your previous slide with all the, yeah. What's this 405 years? I don't understand. It's training. If it takes 50 days to enter all this, say, data, then where does this 405 years come in?
That's the chip count multiplied by the wall clock time.
Oh, okay.
So if you had one chip, that's how many years it would.
Okay. And the cost is not what it costs somebody to buy the system. The cost is what it takes to actually train it.
Well, that's the cost. I believe that's the cost really that the company spends on acquiring the hardware. And what was the size check that was either written to NVIDIA or to Gemini from Google is a little bit different, but that's the prices that people believe were spent in acquiring the hardware.
All right, and this V100 and H100, whatever, those are chip types from, I guess in NVIDIA or whoever, right?
Yeah, all the ones ending in 100, V100, A100, H100, those are all NVIDIA's GPUs.
Okay.
Going from the oldest V100, A100 is a little bit newer, and H100 in this list is the newest.
Okay.
I think it's Voltaire. I forget, A is maybe Ampere and H is Hopper.
Recently, there was this news that so much electricity is also being used,
Correct.
and that's why they have to almost build a nuclear power plant. Can you throw some light on that? Like, why do they? Of course, one can see that it scales in some fashion, but still,
Yeah,
what is
in
going on there?
fact, um, a number of news outlets called me to comment on it. And I don't have my notes in front of me, but the major companies like Amazon and Google, you may have seen, started investing in what's called SMTs. Um, I can't remember what the acronym stands for, but small nuclear, small modular reactors, SMRs. And there are a couple of companies, some in Washington State, some around Virginia, that are starting to build smaller nuclear power plants. And you may have seen Facebook or Meta invested in potentially turning back on 3 Mile Island. And or I could have it wrong. It may have been Microsoft that was looking at 3 Mile Island. So right now, in order to do this training, you need to have megawatts of power, maybe gigawatts in order to do this training. And that amount of power is just not available on the power grid through current sources that we have. The small nuclear reactors, these modular reactors, are getting a lot of attention because they can be built with a lot less regulation. They are able to produce about a third the energy of a traditional nuclear power plant, but they're seen as potentially safer and easier to place around the country rather than building a full-blown nuclear reactor. Now, we don't yet have full approval from the Nuclear Regulatory Commission to stand those up, but everyone believes that that's almost there and that these can be built very rapidly in maybe 3-4 years' time. So some of the companies that are investing, like Amazon and Google, what they've promised their shareholders is that AI will be carbon neutral. So it's very hard to be carbon neutral when you're trading on, traditional fossil fuels feeding these data centers. But nuclear reactors are carbon neutral. And so they have promises by 2030 and 2035 in order to move to energy sources for doing this AI training that would be carbon neutral. I see Alan has his hand raised.
Yes. My suggestion is build the data centers or the AI centers where the power is rather than anywhere. For example, an ideal place to build them would be up in northern Quebec or Ontario next to the big hydro plants. You don't have the losses from the transmission line. You wouldn't have transmission line losses then, and you've got plenty of water for cooling.
I do believe that's the strategy. Excuse me. Many of the tech companies have taken that strategy, and Amazon, Microsoft, Google, etc., have data centers located around the world. And in fact, your applications running in the cloud may be running on the cheapest location to run based on the power, because the cost of power fluctuates during the day around the globe. And so that's already happening in many cases where the traditional power generation from hydro and other sources, I think we're starting to see it tapped out in the country. Our power demands are going to be insatiable for this new AI loads that are coming on.
Except I'd say Northern Virginia is not the place to do that.
Understood, but I think that's where the investments are, and I'm sure there's a little bit of politics and companies and government grants and other things. I don't know the full details, but there's reasons why some of those locations are selected. I mean, right now, many states are trying to build an AI economy and are looking at incentives to locate a lot of the data centers or high-tech personnel within their states or regions. And so we may see some things that are perturbed not by what's best for the planet, but maybe what's best for that particular state or government. So there's some news just a few days ago, and I was able to comment or talk with CNBC about it. But maybe last week, some of you have seen NVIDIA's new announcement at the CES conference that they're going to release a personal AI supercomputer, also called Project Digits. So this is something that will come out probably by May and cost about $3,000, where they're putting one of their Grace Blackwell super chips that includes both their, I think it's 20 cores of ARM processors and their highly capable GPU into a single system on a chip package. There's a picture of it on the right here, kind of blown out. And it would be able to run 1 petaflops if you're looking at just doing 4-bit precision in floating point. Have 128 gigabytes of RAM, and the capability of this box or system that you could have pretty much next to your laptop would be to train a 200 billion parameter model. So many of the models that I've shown on the last couple slides would fit in that 200 billion parameter range, or a model a year or two ago from OpenAI or Anthropic. And if you had the money to buy 2 of these, $6,000, you could link the 2 together and have them work in concert with each other to handle 405 billion parameter models. So this is game changing. This really democratizes the fact that it may not just be these supercomputing tech companies that are spending millions of dollars for training. It may be the case that soon, if you're okay with 4-bit floating point values, that you may be able to have that same capability desktop. Every student could have one of these in a classroom, or companies could build their own models for their own applications and be able to do it affordably with commodity hardware. So this, I think, is game changing, and we'll start to see more and more capabilities and models that people are building very specially tuned to their applications. Any questions before I move on?
Is there any talk of tech transfer to other countries? We're limiting that?
Yeah, there's a lot. In fact, a few days ago, well, as you know, in the past, the Department of Commerce has limited the capabilities of certain countries like China, Iran, etc., being able to use US-based products like NVIDIA, GPUs, Intel processors, and so on. And they've been blocked going into certain supercomputing centers in China, also some companies within China. For instance, NVIDIA is able to give a very old GPU, for instance, that B100 to China, but not the latest H100s to China. And so the US is trying to hold that back. There's currently the Biden administration just a few days ago put some other limitations out there by listing additional Chinese companies that are part of the Chinese, or we presume are part of the Chinese government, and for instance, Huawei and others, trying to limit the technology that goes to them.
Any comments on NVIDIA versus AMD?
Oh, well, first, just to finish up on that comment, I think with the change of administration and those with the ear of the next president, like Musk, that there's going to be a lot of debate about whether or not the US is shoring up our national security versus hindering technological progress. And I think that's going to be hotly debated going into 2025. And there's something to be said about both sides, but I think that's going to be hotly debated. NVIDIA versus AMD both have very, very good processors and capabilities. For whatever reason, NVIDIA hit the market earlier in order to do AI training. And about 80% of the AI training today uses NVIDIA processors. We see that as a bottleneck. As you know, TSMC, the Taiwanese chip manufacturer that does the foundry for most of these processors, including some Intel processors, is trying to ramp up operations in the US. For instance, in Arizona, some new fabs are going to be coming online, trying to get to the same feature size and capabilities of Taiwan, although that may still take a few more years to have that stood up. But I think NVIDIA really has captured the market, but these markets are also very um, robust. And if another company such as AMD is able to put out a capability that is cheaper, more efficient in terms of energy, and cost effective for training, that there's no model lock to a particular processor. The types of operations and software used are very portable. People use TensorFlow and PyTorch to do training, and those run on just about every processor you can imagine. And so there are other companies out there. Notably, there's a company, um, drawing a blank on the name of the company. It'll take me a second to remember the company, but one company is doing wafer scale integration for training. So imagine that you didn't cookie cut chips out of a wafer, but you used the entire wafer, and you could get billions, in fact, now trillions of transistors on a wafer working together.
One thing I noticed recently is the current world's fastest supercomputer, the Titan at Oak Ridge, is using all AMD CPUs and GPUs.
Correct. So let me come back to that. The company that I was mentioning with wafer scale integration is Cerebrus Systems. So it's a very interesting company and architecture. And in fact, they work very closely with TSMC on the physics to do that wafer scale integration. In the US, there's a number of exaflop or exascale supercomputers, Oak Ridge, Livermore, Argonne, etc. Some of the decisions about what processors to make are really to make sure that the US has a diversified supply chain of these technologies. And so the systems, El Capitan at Livermore, Aurora at Argonne, and the systems at Oak Ridge are using different technologies to try to maintain our ability to interchange those CPU and GPU technologies and maintain a competitive advantage by having a multiple supply chain versus just one provider of systems. That's just one of many factors in the selection of those systems. Any other questions?
Let's make one comment. David, I'm NCE class of 68.
Oh, congratulations. That was some time ago, and I was born in 69, so it gives you the amount of time. So in the presentation that I had, I was going to switch gears now a little bit and tell you about some of the work that I'm doing in neuroscience, but also keeping a watch on time, because I know we're at the hour now. But I could spend maybe 10 minutes or so talking about the work that we've done in neuroscience. Is that of interest?
I needed to log off. But can I get these slides possible?
I can share my slides um, with Flash and Don, and they can share them out.
Okay, that will be nice. Thank you. Sorry, I have to kind of go. I would have loved to listen to next 10 minutes as well, but okay. Thanks. Bye.
David, I have one other question. What
Sure.
about inferencing? What are the computational demands for the inference side? You know, after you've got the models built, is that going to be as demanding as, you know, this becomes
It's
more ubiquitous?
yeah, I mean that's a great question. It's certainly very demanding to do the inferencing side because many of the models that occur when you map the model to a particular architecture, you get a certain token rate that you can pull out of the model. So many companies such as OpenAI and Anthropic are looking at that mapping in order to get the fastest number of tokens out of the model. And that, that's a concern when you have one of these LLMs and you're trying to feed a million customers and pull those tokens out. And they look at specialized architectures to do that. Um, it's not as difficult a problem as the training. The training is much, much larger. I mean, as you see, you go from like 130 terabytes to 30 trillion tokens. It's maybe an order of magnitude easier problem to do the inferencing, but it still has an impact in quality of service for being able to pull those tokens out. So it's not as sexy. You don't hear as much about it, but some of the larger companies are doing quite a lot to reduce the latency and also to increase the throughput rates for doing that inferencing. Any other questions? So I'm not going to use all the slides that I had here. I'm going to skip past graphs and just mention one problem that we've been working on is democratizing graph analytics. And this is some work that's been sponsored by National Science Foundation, working with Department of Defense. NSF has supported this project, and we've been building out an open source framework for massive scale data science. Some of you may have known Mike Merrill, who really was leading this effort for building out a system called Arcuda. We work very closely with Mike on this and recognize him for his leadership in this area. But we combined some tools for productivity and performance to help build a system that used a language from HPE called Chapel and let any user with Python be able to do supercomputing back-ended data science. So I'm skipping through a lot of details for this talk. This system was built really for Department of Defense, doing work in cybersecurity and other areas to analyze massive data sets. And for instance, looking at net flow data where you may have packets flying around the internet and you want to be able to understand threats that are coming into your organization by doing some analysis of that net flow data. So we built out the system to do it in terms of graph analytics and then realized that this system that we were building out could also be used for work in the brain connectome. And so I'm really just giving you some highlights and some really exciting things that we've been doing with collaborators, both at Harvard and at Princeton. Here at Harvard with Jakob Treudel, Hans-Peter Pfister, and Jeff Lichtman, they came to us with these massive, massive brain connectomes, and we're able to take in these data sets and do analysis to support neuroscientists based on the exact same code and framework that we built out for the government. So it's a fascinating area that we've been working in for maybe the last year. And in fact, recently, the very first full brain, this is a Drosophila or fruit fly, was created where every single neuron is labeled in the brain. So this is a brand new area of science that's just really, really phenomenal and breaking, where we have the connectivity, the geometry, the topology, and type of every single neuron in an entire brain. And you can start to pick out areas of the brain, such as the optic processing regions, sensory processing. Um, we'll see more visual projection and so on. So it's a fascinating, fascinating area. And I'm kind of glad that we've been able to be ready to support the neuroscientists with code that we built out for cybersecurity. What we get are 3D images of brains, or the brains with their neurons, their axons at each nerve, and then the dendrons, um, and the uh, um, let me go back here. The axons and dendrites that connect. And we see the synapses where information is exchanged between the brains, usually in some direction, either through chemical means or through electrical means, or some other processes. And we can start to ask questions or find patterns in the brain. And these are getting to be very large data sets. In fact, today we're working with this H01 data set, about 1.4 petabytes, that is from a fruit fly. And in a few years, we'll likely be able to have a full mouse brain. And from the full mouse brain, we'll understand more about how brains like humans work, versus a fruit fly is a little bit further from a person. But a full mouse brain is probably about an exabyte of data, and we can store an exabyte of data. Today, it's a very large data set, but we're actually getting to the point where we may be able to have this full mammal brain, and do some more understanding. So here's that H01 data set from the fruit fly. There's about 57,000 neurons and about 133 million synapses. It's a big directed graph. And we often assign each neuron to a vertex, and the number of connections or synapses between the vertices. We create a directed edge with that weight. So it's a highly, highly connected graph. And what we're trying to do, for instance, is to work with neuroscientists who are looking for some pattern inside the brain. And we're doing algorithms like pattern finding or pattern matching to find occurrences of that type of pattern with those types of neurons in the brain, among other things. So this is a need where neuroscientists may say, I have these 4 types of neurons. I'm looking for anywhere in the brain where they communicate as follows. Ordinarily, this problem would be NP hard, intractable on data sets this large, but we're working on algorithms and using supercomputing to try to solve these types of problems, and we're doing it quite successfully. I think here, this is a variant of that problem where we're looking for particular small structures, and today we're able to run, this has 1 to 2 orders of magnitude. Today, we're up to about 2 to 3 orders of magnitude faster than the current tools that everyone uses in Python, like NetworkX or dot motif, to find these types of structures. So we've been working very closely with neuroscientists at Harvard, at Princeton, at other places to implement more and more algorithms in this open source framework to do these types of analyses in this emerging area of neuroscience.
What programming languages are you using?
Oh, so we're using at the core, if I go back to this slide, what we built out for the government, Chapel, which is a parallel programming language, maybe a superset of C++, that makes it very easy to do parallel programming. And the user is using Python at the front end. So the user is just interacting with the Jupyter notebook in Python, but what we built out on the right hand of this slide is using Chapel, that came out of the DARPA High Productivity Computing System program when Cray was a company that HP more recently acquired. It was Cray's Chapel programming language, that has its origins from about I guess, 2010, so that's about 15 years ago. And if I go forward here, this is how a user may write their code in Python. It's just some simple Python, and this runs a couple graph analytics, loads in a graph, and does some analytics. So the user themselves don't need to know high performance computing. They don't need to know anything about supercomputing, but they can run this with a supercomputer in the back end and scale up to these massive tens of terabytes data set sizes without having to know anything different than how they run with Python on their laptop. Does that answer your question? So I'm giving you the very abridged version of what we're doing for the sake of time. Normally I could talk for hours about the architecture and the system, but we're really trying to here democratize the ability for anyone to do both data science and graph analytics on massive data sets without needing proprietary languages or software or systems, but anyone anywhere should be able to run these types of algorithms. We have a number of papers on different graph algorithms, and all of this is open source, including the Chapel compiler from HPE. The entire software stack is open source. Again, lots of publications. And finally, my last slide is really recognizing my research group, including my PhD students, undergrads, even high school interns who have been contributing to the work that I presented here in the last few slides. So I want to thank all of you for paying attention. I love the interaction of the talk here, and I'd be glad to answer any remaining questions.
Yeah, I have a question. If you put your education hat on, I've heard there's worry that because this is so expensive, the universities will have a hard time being at the leading edge because they just don't have the money. Do you know how, if you can have some kind of partnership with industry, or what do you think the future is?
So I completely agree. And most leading academics are leaving academia or either full-time or consulting with some of the top tech companies to do the leading edge research in the AI space. I think that it is very hard or impossible for universities to compete, and no funding agency is willing to give a university $1 billion to do this, but companies are willing to pay that. And I think it's exactly as you said, finding partnerships or academics finding part-time appointments. For instance, Amazon has a program called Amazon Scholar, where an academic can choose a portion of their time to be a full-time Amazon employee and do work at Amazon and maintain a certain percentage at the university.
Oh.
NVIDIA Project Digits, I think, is very interesting because that for the first time gives some really amazing capability at an affordable cost to universities. So I do think that will be game changing. It probably won't be able to build the largest trillion or 5 trillion parameter models, but 200 billion parameters is enough for most in academia to be able to write papers, to build a system, to have students trained on it, and so on. But I do think that this is a very expensive game, and universities are just not going to be equipped to be able to compete in this area.
Do you think something like a national lab, like Oak Ridge or something, but centered on AI, where a large number of people could use it or come and be students for a while and take advantage of it?
I do think the national labs have some very interesting problems. In fact, Rick Stevens at Argonne is looking at doing a very incredible study on cancer using AI. And there are many things that may not have as much of a commercial interest that the national labs could focus on, such as what Rick is doing, and be, really worthwhile for our taxpayer dollars and accomplish great science and build these large AI systems. So I do think the national labs have a huge role to play. It's really going to be to sustain that investment. As you see, right now, the way the US government gets funded, it's very hard to have sustainable funding. And some of these projects really need that continued investment. In fact, I work with the government for years and years and years. And right now I'm in a gap for funding, and I don't know, do I fire my whole team or do I wait another week because maybe the money will come in? And then November 20th, will it still come in? Will things change? It's very hard on government funding to sustain this versus our competitors, including nation states, have continued investment. And I think the US is really challenged the way we fund large efforts to be able to really invest what's needed in this space.
Thank you.
You're welcome.
If there's time, I have one final question. You're using massive data sets, massive amounts of parameters. How much does Ramsey theory play into all of this?
That's probably beyond my expertise.
Oh, okay. I mean, it's a fascinating thing. Ramsey, 100 years ago at Cambridge, proved that any data set has unintended correlations in it. Might not be a surprise. So, and I would worry that you could fall into a trap by obviously trusting too much what these things spit out.
Well, I think that's a lot of where the hallucinations are, because there's a lot of strong correlations that are spurious. And that's what you're getting, things that look right, but the data says these things are correlated. And at the end of the day, these are just massive, massive correlation engines. Here's a token, tell me what you expect to see next. And so I think we're pulling into that trap. And also, when the first models were trained, they're using quote unquote pristine data. Now, as new models get trained, they're using potentially output or polluted output from LLMs.
Right.
And it may be hard to differentiate. Imagine you're training on email. All email before 10 years ago was not AI generated. Today, I don't know what fraction of email, but certainly there's some email that's AI generated that I can't differentiate between. So there's some thought that more and more training is actually going to be worse for these models as they start to ingest their own output.
Yep. Yeah, well, if you want to see an interesting thing, look up spurious correlations if you haven't seen that.
Oh, I love it.
I love that site. It just cracks me up. So okay,
I use that every year with students. I show that site and
that's
look
perfect. That's perfect. Yes.
The price of cheese versus the number of pirates attacks.
Yes, exactly. Yeah.
Alan?
You had a figure for the number of synapses, I believe, in a mouse or some other connection metric.
Yes.
What is the figure for a human brain?
Oh, so I think Wikipedia will probably get that faster than I will. And there may be some debate on it as well. But well, I actually visited the Princeton Neuroscience Lab, the lab of a few of the researchers there. They're doing the imaging, and it's really fantastic how they're doing. They take a brain, they encapsulate it in resin, they use a micro slicer to it, and they get these little discs out that they put on a paper tape, and then they run that tape through a is it a transform electron microscope, and
Transmission.
transmission. And they take for like 1 fruit fly brain, it may take them about 2 or 3 years to do that whole process. And they may get, they're experimenting with how big those slices are. You can probably look at Wikipedia faster than I can to figure out the number of neurons in a human brain. I don't remember it at the moment. But the issue is that we can do this on Drosophila and a mouse, but to do the imaging today, you have to decimate the brain. And so unless you have a friend who's willing to volunteer their brain for science, it'll be a long time before we see the image of a human brain, although maybe there's a volunteer. But it's the actual size that can be imaged. The amount of data that they're generating is massive. So we don't think we'll see a human brain in the next, say, 40 years, only looking at the size of storage needed to store the scan and the length of time it will take on today's electron microscopes to do that imaging will take an extremely long time. So today, maybe a square millimeter of brain matter can be analyzed in about a year's time. And so if you think about our brains, it would still take a very, very, very long time to get a human brain done. And also, that's just one fruit fly. We don't know if it was a mentally ill fruit fly, if it was a happy fruit fly. We're just starting to work on problems of multiple, like a male versus a female fruit fly or stages of development. And we've been working with Princeton on some algorithms to do things that haven't been done before, like comparing a male to a female brain. Princeton has a competition right now looking at the ventral nerve cord of a male and female fruit fly, and we're trying to figure out the graph matching to even decide what is normal in the brain, what is different between the two, and so on. So there's a lot of science, a lot of algorithms needed. Last summer, I was invited to Germany to a Connectomics conference of PIs working in the space. Out of 200 people, I was the only person who was a computing person. So there's not a lot of computer scientists involved yet, which is great for me. But there's a lot of thought of how to optimize these algorithms. I have a friend at Princeton, Ari Matzliak, where we talk pretty much every week, brainstorming algorithms to try to do this connectome analysis.
Well, the question I have is, of course, this is all very interesting scientifically, but what's the politics? Who will eventually control all this capability, and to what purposes will they apply it? And is there any control that society can put on it? This is going to be the problem.
That's a great question. In fact, I've been on a state of New Jersey task force looking at how the state of New Jersey is going to handle it. And it's very, very complicated because the technology is moving much faster than any politician could understand.
Exactly.
And so I think it'll be a number of years, 3 to 5 years, before we start to see some, real national guidelines or thoughts or outputs on this. It's a very, very important question. I also don't know how the next administration is going to treat it.
Yeah.
Or not treat it. So I imagine that in the next administration, business, which already has been able to move faster than regulation, will probably continue to do so. You've probably seen individuals suing these companies because their copyrighted works, whether it's the New York Times or, authored manuscripts, are being spit out of these LLMs. We would have thought that would have slow down some of the actions that are taking place in terms of learning. Not really. I mean, so far things are moving ahead, and the courts have sided with this innovation and national competitiveness over copyright law.
Yeah, I mean, as a kid, I can remember reading Isaac Asimov's robot stories, you know. And in science fiction, it always comes with a happy ending, but you know, in real life, usually power politics and greed and whatnot is a major component in some of this, and that's what worries.
I'm not worried about AI taking out humanity. You know, at the end of the day, we can always unplug it. So I'm not as worried
Yeah,
as that. But
what
what
I'm
I'm
saying is, who controls the actual infrastructure and to what purposes will they apply it? This is still a serious question.
correct, and I think you know people have to have those conversations. Um, but right now, it's very hard because understanding the technology, people can't differentiate between a search engine and an AI, for instance. And so it's going to be very, very hard to have those types of discussions, but I think they're going to be necessary.
I'm worried about data centers and Bitcoin being used for money laundering.
Right. I mean, I think in the years to come, we're going to see some colossal engineering failures that are then going to cause people to look back and say, "Oh my gosh, how could we have allowed Boeing to use this piece of code, or how could we have allowed not picking on Boeing, but you know this airline company, or how could we have built these bridges using this concrete where the formula came from this AI and so on." And people are going to work backwards and say, maybe we should have you know, watch this a little bit better. And I think it's not until we see a couple of colossal failures, which will happen, that we see more regulation about the use of LLMs. Just my opinion.
Yeah, yeah, exactly.
Well, again, thank you. I'd love to entertain any more questions, but you know, this was fascinating. It's not often that I get to give a talk with so many you know, educated people with these broad backgrounds and have it interactive like this. I really, really enjoyed it.
Thank you very much for a very entertaining talk.
Yes, yes. Thank you very much.
Thank
Excellent.
you so much. Great
We,
talk.